Let me introduce him briefly. So I'm delighted to have Riccardo Bianchini today giving the first keynote. He's a distinguished engineer at Microsoft, where he leads efforts to improve cloud efficiency. He also leads the systems research group at MSR in Redmond, and he has published 9 award papers and received the Career Award from NSF. He has also served on numerous program committees, including as program co-chair of ASCLOS, Eurosys, and ICDCS. And he's also a fellow of the ACM and the IEEE. And he will talk to us today about serverless compute, which is a topic you will see prominently throughout the whole duration of the conference. So Riccardo, whenever you're ready.
All right. Can you hear me okay?
Yes.
All right. Thank you very much, everybody, for attending today. And thank you, Christina and the other organizers for having invited me to give this talk. It's really an honor for me to be here talking to you today. So what I'll talk about today is some of the work that we've been doing in my group in trying to make serverless computing the future of the cloud. And this is not really just my work, it's a collaboration, a wide collaboration with people from MSR and researchers and students from many universities, Stanford, Berkeley, Princeton, Cornell, Purdue, and several folks from the Azure Functions team. So let's jump right in. Before any serverless computing talk can start, we have to define what we think about serverless computing, as this is a very overloaded term, right? So what it means to me is a cloud computing abstraction that where the user can essentially doesn't have to provision resources, doesn't have to configure resources, like say create VMs and define a number of VMs, configure their VMs, and so on. And scaling comes for free, essentially, or from sort of auto scaling comes built in. And scaling is essentially infinite to the extent that you can go from no resources at all to as many resources as your application might want and back, and all of that automatically. And also very important is that the user pays for the use of resources at a very fine granularity, rather than paying for resources that they actually allocate. So today, the most popular offering of serverless computing is called Function as a Service, or FaaS. And in FaaS, what you have is bounded time functions that have no persistent state across invocations. And for that reason, we call them stateless functions, in the sense that if you want to keep state from one invocation to the next, you really have to store that state in some remote storage medium or event queues, message queues, and so forth. So the functions execute when they're triggered by different types of events, say HTTP requests, timers going off, an event queue or a message queue, those types of things. And basically the way to interact or to create functions to execute is very simple. One sort of uploads their code to the serverless provider. The serverless provider gives them an endpoint. Let me actually get my laser pointer here. So you have like a very simple function code. You submit it to the serverless provider that gives you an endpoint, and then users just go and execute the function at that endpoint, and like multiple instances of the function get created as more users come to use it. So for the rest of the talk, I'm actually going to talk about serverless and serverless FaaS interchangeably, right? So whenever I say serverless, think of serverless FaaS throughout the talk. So another way of looking at serverless computing is as an evolution of the cloud. So what I'm showing you here in this table on the left side is a number of characteristics of these different stages of evolution of the cloud. So we started out with bare metal servers, and the more senior folks here might remember what we called hosting centers, where people deployed their physical servers that were operated by a company, very similar to what we call leasing centers today. So that was the very first stage, and at that point, the unit of scale was an entire server. The scaling involved buying new hardware. The typical lifetime was years. The payment was per server, and the state could be anywhere. So after that, we started deploying VMs to the cloud, and this is what we normally think of the cloud. The unit of scale then became VMs, not full servers. Initialization time was shorter. Scaling was done through allocation of VMs, and so forth. Then we moved on to containers that made things even easier and faster. And now we're finally at the functions or function as a service stage of evolution, where the unit of scale is a function. The provisioning is the responsibility of the serverless provider, or creating the resources for those functions to execute in is the responsibility of the provider. Initialization time is a few seconds. Scaling is from 0 to many and back, as I mentioned before, automatically. As you'll see later on, the typical lifetimes are very short. And payment is per use, as I mentioned, and state, again, has to be elsewhere, not associated with functions at this point. So state is one of the issues that a lot of groups are looking at, how to endow functions or function as a service with state. So this is how things have been evolving. And because of these nice features of serverless, there has been a lot of attention towards serverless computing. And here you can see a number of headlines from the IT press talking about serverless in the same terms that I'm talking about serverless today, like why serverless is the future, or why serverless is the future of software and apps, and so forth. So there has been, a lot of hype out there in the IT press. Similarly, there have been, a large number of serverless papers published so far. And this conference is a good example of that. And in particular, I'd like to highlight this early paper from Berkeley, where they actually state that they predicted that serverless computing will grow to dominate the future of cloud computing. So again, a lot of interest in serverless, and a lot of people thinking that it can be the future of the cloud. And as a result of all that interest, as you would expect, there have been a number of platforms that have been created, either hosted platforms or installable platforms. Among the hosted ones, we have AWS Lambda, the first one to be created in 2014, but also Azure Functions, Google Cloud Functions, IBM Cloud Functions, and so on. In terms of installable platforms, you have pretty popular ones also, like the open source OpenWhisk system that actually forms the basis for the IBM Cloud Functions offering. So as you can see, the serverless ecosystem is growing significantly, and there's more and more people trying to use serverless computing. Now, what are users actually doing with serverless? Well, it turns out that they're doing many useful things, but they tend to be quite simple things, right? So for example, extract, transform, and load workloads, IoT, sensors and data collected from sensors and receiving some light processing, many types of stateless processing, such as image, video encoding, translation, and so forth. And also serving as backend APIs for mobile and web backends. So people are using serverless computing, but things are still fairly simple. However, there have been some promising explorations already where things like parallel computing and even more challenging things like ML training for serverless have been studied. So for example, PyRen came up with MapReduce for serverless computing in the context of Python. And you have other examples like NumPyRen for linear algebra, XCamera for video processing, and so forth. Now, the reason why serverless today has a number of limitations that has constrained the set of initial applications that we've seen. And I'll mention some of these limitations here. First one, the stateless characteristic of serverless is a main one, right? So whenever, as I mentioned, we want state to persist from one invocation of a function to the next, that state has to be kept in some remote medium, such as remote storage service. And because of that, there's also a problem with high latency for some applications because the data is remote. Another significant source of high latency that I'll talk a lot more about later on is the notion of cold starts. Cold start essentially happens when an invocation comes and the serverless provider is not ready to provide not ready to execute the function right away. It still has to prepare the environment, bring the function into memory, and do a number of things that also might take a substantial amount of time. So I'll talk a lot more about cold starts later on. Another problem is that oftentimes there are I/O bandwidth constraints. For example, the execution of a function might be constrained by the amount of bandwidth that the underlying VM might provide, or it might be constrained by the fact that other functions that are co-located with it are consuming most of the bandwidth, the I/O bandwidth to the outside. So finally, there are issues with communication and addressability. So in most cases today, it's not possible really to address another function and communicate directly with it. So again, communication has to happen over a remote medium. So these are just a few examples of limitations. There are more, like the bounded time execution of functions, and people have been working to eliminate these limitations, or at least mitigate them. So these are some of the reasons why there are a number of applications today that cannot run still on serverless computing. So what about the serverless provider? From the point of view of the serverless provider, and note here that I'm drawing a differentiation between the serverless provider and the cloud provider, right? The serverless provider is the entity that's responsible for renting resources. They're typically VMs, but they could also be bare metal servers from the cloud provider to then provide fast on top of those resources, right? It turns out that the serverless provider actually has to worry about many of the things that the user doesn't have to worry about. So it has to do provisioning of resources. It needs to do scaling, to do allocation of resources when they're needed. It needs to secure and isolate customers from each other. It also needs to provide this notion of infinite scalability with obviously a finite amount of resources, right? It needs to trade off cost and performance, right? So it's easier to have high performance, for example, if you keep all functions in memory at all times, but obviously that has a high cost. Similarly, there's a trade-off between cost and security, right? The way to make things most secure is never to have multi-tenancy or have, you know, two functions of different customers in the same VM, for example, which if you don't do that, you get great security, but costs again go up. So the cloud provider, the serverless provider, actually has to optimize its resource usage by doing tight packing, using multi-tenancy, and so on, so that it can lower its costs. And in this area, competition is really fierce. And if you're not careful, Amazon Lambda will eat your lunch, right? So what we're interested in our research is we're interested in addressing the limitations from the previous slide and the challenges from this slide, so that we at the same time broaden the scope of applications and make the serverless provider become cost effective. So now, how do we look at these two dimensions of improvement to serverless? Well, let me start with where we are today, right? As I mentioned, there's a fairly simple collection of apps, or a collection of simple apps that are being executed. Today, serverless represents a fairly small fraction of the overall load of cloud systems, and the price that's charged to the customer typically doesn't reflect the actual cost of providing the service. So in one dimension, we want to broaden the scope of applications by looking at ways to improve performance, maybe by providing new abstractions of systems, new tooling, and perhaps system and hardware support, as well as looking at improvements to programming models with things like enabling orchestrations, enabling critical sections, and so on, things that are being studied today and provided by things like by systems like durable functions and step functions. So we are a systems group, so we tend to focus more on improving performance, the improving performance side of things, and not so much on programming model improvements. So this is one dimension, right? This dimension, the goal here is to try and make the set of applications that are feasible and perform well in serverless become broader. In the other direction, we want to improve resource efficiency, again, so that we reduce the cost for the serverless provider. And here, what's involved in improving efficiency is a number of things, and some of the ones that we're looking at so far are predicting workloads, minimizing resource usage, potentially running on spare resources, and leveraging tiny VMs. Only with progress in these two directions will we be able to eventually achieve a future where serverless is broadly applicable and a major, or sort of the main component of the cloud. So what I'll talk about for the rest of the talk, first will be techniques that we've created to minimize resource usage in the management of code starts, and we'll do that via predicting workloads. And I'll also describe a nice and clean abstraction that we use to do the workload prediction. Later on, towards the end of the talk, I'll also talk about some of the additional work that we're either doing now or that we envision doing in the future. And that will have to do with running on spare resources and using tiny VMs, and also in terms of new systems, new tooling, and so forth. So here is the roadmap for the rest of the talk. I just covered the introduction to it. Next, I'll talk about improving performance and efficiency. And I'll start with the workload characterization. We figured that the first thing to do in sort of trying to improve performance and efficiency is really understanding what the workload is like today. And then I'll present our techniques for reducing the number of code starts and the resource usage at the serverless provider via workload prediction that's inspired by the workload characterization that I'll talk about. After that, I'll talk about our current and future work, and then conclude the talk. So jumping into the workload characterization, it turns out that when we started this work, there weren't any papers characterizing the workload of serverless providers from the provider's perspective. There were a few papers that tried to sort of reverse engineer what was going on in the serverless provider and its performance and so on from the user's perspective by sending functions to be executed and observing their behavior. So we figured we would do a full characterization of the Azure Functions workload. And that work became this paper that came out in ATC and received this community award because essentially we made traces available from that data set available at this GitHub site here. And I encourage people to go here, get our traces, and do their work using that the data that we provided there, because it's representative of what you see today in actual function offerings, function as a service offerings. So before I tell you about the results of the characterization, I need to tell a little bit more about what Azure Functions is and how it works. So functions in Azure Functions can be written in many languages, such as C#, JavaScript, Python, and so forth. The functions have the multiple triggers that I had mentioned before, the ones that you would expect. There's actually quite a number of variations here because there are multiple types of event queues, multiple types of timers, and so forth. And storage substrates as well that can be used. But for the purposes of our characterization, the key aspect of functions is that functions in Azure Functions are actually grouped into applications. And the application is the unit of resource allocation and scaling. So whenever you need more instances of a function to execute, what you're actually creating is an instance of the full app with all the functions that are part of that app. So we tried to answer a number of questions in a workload study. And some of the key ones are listed here. For example, how frequently functions are invoked, how many functions form each application, how are functions triggered, what are the different types of triggers, and how are they combined, how popular they are, and so forth, how long functions take, and how much memory they consume. So during this talk, I'm not going to have time to go over all of these, the answer to all of these questions, but I will address 3 of them. I'll start with how frequently functions are invoked, then talk about how long they take and how much memory they consume. So let's jump into that. So here, I want to talk about the invocations per application, and this is for a representative subset of our workload. So on the x-axis here, I'm showing you daily invocations per application in log scale. On the y-axis, this is a cumulative, the cumulative fraction of applications that have these daily invocations. So what you can see first is that on this side here, we have the less frequently invoked applications, or what we typically call the less popular or unpopular applications. And on the right side, we have the most frequently invoked applications. And as you can tell, there's an 8 to 9 orders of magnitude difference between those two ends of the spectrum. And what that means is that it's pretty hard to actually build a system that's efficient and effective for, you know, this entire span of applications. So another interesting observation here is that these vertical lines actually represent, you know, some specific intervals between invocations. So on the left side, on the right side here, we have 1 second, then 1 minute, 5 minutes, 15 minutes, and so on, up to 1 day. So these applications here, about 20% of applications are invoked on average less than once a day, right? So if we, okay, move Christina here. So if we look at this point, for example, right, we have 45% of applications that are invoked on average less than once per hour. So we formed this group of applications here that we color green. Over here, we got 82% of applications that are invoked on average less frequently than once a minute, right? And this includes the green group as well. And it's this whole area here, 82% of applications. And then finally, there's 18% of applications that are the most frequently invoked, and they're invoked more frequently than once a minute. So you see these three groups here. So why don't we flip those two axes and let's look at them with the percentage of most popular applications on the x-axis and the cumulative fraction of invocations on the y-axis. And note here that I kept the color scheme the same as in the previous slide. So the red area here, this group of applications up to this point, is the 12% of applications that are most frequently invoked. And the yellow and green here are the ones that are least frequently invoked. What's interesting about this is that the actual fraction of invocations for those 82% of applications is really small. It's only 0.4% of invocations, whereas the other 18% actually correspond to almost all of the invocations, 99.6%, right? So even though these are the most popular by far, and in terms of invocations, they are almost all the invocations, most of the customers are really behind these applications. So we got to find ways to achieve good performance for those applications with an efficient, reduced amount of resources for them. So now let's look at, in more detail, at different applications and how they behave in terms of their invocation patterns. So here I'm showing you one application, and the font here is pretty small, but it's not important. What I'm showing on the x-axis is the arrival time for the invocations. And on the y-axis is the inter-arrival time of those invocations. And each blue dot here corresponds to an invocation. So as I mentioned, it's not that important to see the details of the graph, because I just wanted to show you how different applications can be. Over here, you see one with lots more invocations and sort of very heterogeneous behaviors. Similarly, over here, very different behavior for this one as well, and so forth. So what this shows is that these invocation patterns are quite heterogeneous, and sometimes even within the same application, you can have invocation patterns changing over time. Okay, so what about the amount of memory that these different types of applications would consume if we were to keep them warm all the time, or keep them in memory all the time? So in this graph, I'm showing you the fraction of least invoked applications. So these are the least invoked ones. These are the most invoked ones, or most frequently invoked ones. And this is the cumulative fraction of total memory. And I show two curves, one for allocated virtual memory, and the second one, the blue one, for physical memory that's consumed. So it's interesting to see here that those 82% of unpopular applications would actually consume about 40% of the physical memory. And worse yet, if we were to go to around 1% of applications or invocations, it would represent about 90% of applications, and we would be consuming 50% of all the physical memory. Again, these are infrequently invoked functions, so consuming half the amount of memory for them seems like a very steep cost to pay, right? So we need to do better than this. Finally, let's look at function execution duration. On the x-axis here, I'm showing you time, and this is a CDF graph with the durations. So I'm showing 4 different curves in the graph, one for the minimum out of the invocations of the function. What is the minimum duration? The average duration, the maximum duration, and a log normal fit, just because it fits so nicely with the average. So what we can see here is that 50% of the functions on average run for less than a second, right? So they're on average, they're very, very short. And 75% of them run in less than 10 seconds maximum, right? Again, another indication that they don't take very long at all to execute. And this is quite different than what you normally see out there as you are deploying VMs or even containers. So the more interesting observation here is that these durations are actually comparable to cold start times, which range from 200 or a few hundred milliseconds to a few seconds. So what that means is we really have to optimize cold starts, because otherwise the cold starts become start to represent most of the time that you have to wait for your function to execute. So what are some of the key takeaways from the study? Number one, that the invocations are highly concentrated, right? So we need to provide good performance for applications that are not invoked very frequently, but we have to do it at a much lower resource cost than keeping them in memory all the time. The second main observation is that the invocation patterns are highly heterogeneous across applications, and sometimes even within applications. So we need to come up with techniques for managing resources, and they should be per application, if at all possible, to account for that heterogeneity. The third key observation is that execution times are very short, so code starts cannot be neglected. So we like I mentioned, we put our traces we made them available publicly, but there's still a significant need for real workloads, actual code that people can run and modify and so forth. And I encourage the community and also my industrial colleagues to try and work on that and make those available to researchers and practitioners. I know that we in my group are looking at that as well and trying to create like benchmark suites that can be made available publicly. Okay, so that covered the first part of the talk, the workload characterization. Now I'll talk about how we use the insights from the workload characterization to create a technique for managing code starts that reduces the number of code starts, as well as reduce resource usage using workload prediction. So let's go into more details on code starts, what actually happens on a code start. And this is a little high-level representation of what happens in Azure Functions, where resources get, a worker gets initialized and specialized to run functions. The files mounted to the worker and so forth. Then the function runtime resets. There are some more files read and so forth. Then the actual function code or application code gets loaded into memory, and only after all of that happens, the code runs. And this is similar in other systems as well, like OpenWhisk and AWS Lambda. Turns out that this whole process, you can optimize it a little bit and so on, but it's still a significant overhead. So there are two approaches to managing code starts. One that has received quite a bit of attention is making code starts faster by maybe pausing functions or containers and doing other tricks to start up faster. And another direction where people try to reduce the number of code starts to begin with. And this is the variation that we took, and then I'll talk about next. So let's think of code starts and resources, right? It's really a trade-off between the number of code starts that you're willing to take versus the amount of memory or other resources that you're willing to consume. So let's look at the extremes. We can sort of try and keep all the function instances in memory indefinitely. And this would give us a very low number of code starts, because only the first time that a function is used, it would have to be loaded into memory. But the wasted amount of memory would be very high. At the other extreme, we could remove a function instance from memory or unload it from memory after each execution, right? This would have a very low amount of memory waste, but the number of code starts would be very large, because every invocation would mean a code start, right? So clearly we want to be somewhere in between, and you can think of a Pareto frontier over here that we would like to move as close to the origin of this graph as possible, right? So that we have the least amount of code starts with the least amount of wasted memory. Now, a question you might ask is, well, given this trade-off, where or what do serverless providers actually do? Well, it turns out that the way they handle this is they unload an instance after X minutes of idle time. So in AWS Lambda, X is 10 minutes. So if a function is not used, not invoked for 10 minutes, it gets unloaded. And in Azure Functions, it's 20 minutes. So an application that doesn't get any invocations over a period of 20 minutes gets unloaded. So we call this type of policy the fixed keep alive policy. It's the same amount of idle time for all applications, regardless of their invocation patterns. So let's look at how it works in more detail. So here I'm showing a figure for a 10-minute fixed keep alive, or that of AWS Lambda. And I'm showing you a function that gets executed every 8 minutes. It is potentially triggered by a timer. In the first invocation is a cold start, but the second and third, because they come within 10 minutes of the previous one, then those are warm starts. Now you might have a different application for which the interval between invocations is actually 11 minutes, just above the 10-minute fixed keep alive. And you end up with cold starts for every invocation, right? Clearly, the fixed keep alive policy does not fit all applications nicely. Turns out that it's also pretty wasteful, right? So going back to that example where we have invocations coming every 8 minutes, during those intervals, during those 8 minutes, the function image is actually kept in memory, but not used at all, right? So this is extra memory that we could, or wasted memory that we could try and get rid of. So given these limitations of the fixed keep alive policy, we decided to come up with a different policy that we call hybrid to reduce cold starts and resource usage at the same time via per app workload prediction, or per app invocation prediction. So the policy is inspired by our characterization, and the key principles are these few principles here. One, that we'd like to adapt to each application's invocation pattern. And while that pattern is unclear, we use a fixed keep alive policy to keep it simple. But when the pattern does become clear, then we do a per application pre-warming. And by pre-warming, what I mean is that we will unload the application or the function, if you're thinking about other serverless providers other than Azure Functions. You unload it after an execution, and then pre-warm it just before the next invocation is going to come. So that's what I mean by pre-warming. You bring it to memory just before the next invocation. And then you keep it alive, waiting for the invocation to actually come. So I'll show you this in more detail. So there are like two types of behavior depending on whether a pattern is clear or not. And the other key principle behind our policy is that it really had to be very lightweight, right? Because it needed to be practical and very lightweight so that it could actually be used by an actual serverless provider. So to create this policy, we created this nice and simple abstraction to represent the idle times between invocations, right? From the end of an execution of a function to the next invocation. That is what we call the idle time. So here we have a first code start at time 0, and then 8 minutes later, we have the other invocation in this example. So our histogram would record that there was one idle time of 8 minutes. Then for the second 8 minutes, it would again add that to the histogram, right? And you would keep doing that over and over over the course of the execution of the application. So you might end up with a histogram that looks like this, right? Where we see idle times of 7 minutes, some idle times of 8 minutes, some idle times of 9 minutes, right? And it turns out that if you represent the idle times in that way, then it becomes very clear what those two parameters need to be: the pre-warm time, which can be this amount of time here, 6 minutes, and the keep alive time. That could be the difference between these two numbers here, right? So 3 minutes, right? Because we know that no invocations come in less than 7 minutes idle time. So we can we can unload the function or the application for 6 minutes and then bring it up. And then because the idle times can be 7, 8, or 9 minutes, we wait for 3 minutes for the invocation to come, right? So now a natural question would be, well, is it enough to just track the minimum and the maximum idle times? Or why do we need an actual histogram? Well, the reason is that you want to be a little smarter about setting these two key parameters, right? For example, you may want to disregard some outlier short idle times in your pre-warm definition. Similarly, you may want to discard some outlier invocations that are very long so that your keep alive is not excessively long and wasting memory unnecessarily. So in our experimentation, we actually used, we put this cutoff here at the 5th percentile of invocations and this cutoff here at the 99th percentile. Those two are the ones that showed the best results overall for our data set. So you see the idea of the histogram. Now, you know, how wide should this histogram be if we make it into minute-long bins and you go for histograms of 4 hours, for example? This would mean just 240 bins, or roughly 1K of storage per application. So, but what happens if there are invocations that are longer, or idle times that are longer than 4 hours? Well, in that case, we need to record the number of those invocations that are out of bound, and there might be a lot of them. And if it turns out that the amount of invocations with idle times over on this side is large, maybe we should do something different, right? For these applications, we actually can afford more complex predictors than a simple histogram because the arrival rate is so low. And a histogram that would be this wide would be wasteful, right? So in that case, we end up using time series forecasting, and in particular, a RIMA modeling to address applications of that type. So to see overall what the hybrid policy looks like, we get new invocations over here on this side. And then the policy is going to decide, first is going to update the idle time distribution for that application. And then it will decide, do I have too many out of bounds idle times? And if there are too many out of bound idle times, it uses a RIMA, as I mentioned before. If there aren't too many out of bounds idle times, we check the pattern of invocations to see if it's significant. So we look at the histogram that has been produced so far. And if it's not significant, we are conservative and use a fixed keep alive policy. But if it is significant, then we use the histogram to decide what to do and whether to unload, what the keep alive should be, and so forth. So now let's look at some results showing the performance of these policies in terms of both code starts on the x-axis and wasted memory on the y-axis. So here, this graph is very similar to that cartoon I showed before, where we're looking for a Pareto frontier that was close to the origin, right? So here I'm showing just the third quartile of application code starts. This is a little hard to represent. So let me show you what a couple of these points mean. And here I'm drawing the Pareto frontier for fixed keep alive policies of different durations, where the X is either 5 minutes, 10 minutes, 20 minutes, and so forth, right? The X that I mentioned before. So let's see how to read this graph. This point here means that with a 5-minute fixed keep alive policy, 75% of the apps experience less than 65% cold starts, right? This is 65%. And the 75% comes from the fact that this is the third quartile of application code starts. Over here, for example, this point represents the 2-hour fixed keep alive policy, where 75% of the applications would experience less than 20% cold starts, right? So hopefully it's clear what this graph means. Now, how does the hybrid policy do compared to the fixed keep alive policy? It turns out that it produces this other Pareto frontier here that is substantially better than the initial one for the fixed keep alive policy. And here I'm showing different points for histograms of different lengths, from 1 hour to 4 hours. So to read the figure here, in terms of the comparison, we can say that the 4-hour hybrid policy can achieve the same cold start percentage as 120 minutes of fixed keep alive policy, but only using 2/3 of the resources, right? Another way of looking at the results is that we can achieve less than half of the cold starts with 15% fewer resources than the 10-minute fixed keep alive policy. By the way, I forgot to mention that we're normalizing here the wasted memory to the value for the 10-minute keep alive policy of AWS Lambda. So you can see, as I mentioned before, the Pareto frontier is much better in terms of cold starts and resource usage. And it turns out that we've gotten the policy, or at least the initial implementation of the policy, implemented in Azure Functions and running in production, and it's been showing really good results so far. We've had 36% of the HTTP triggered applications be pre-warmed with 97% accuracy. So it's doing pretty well in production, and the nice thing about it is that it's very simple and very practical to use. So what are the key takeaways of this second part of the talk? First, that it's possible to reduce the cold starts and the resources at the same time. And the key to doing that is to try and predict the idle times for each application independently. We created this very simple and practical abstraction that clearly represents the two main parameters in trying to predict idle times, and created a policy that leverages those parameters to reduce both code starts and resource usage. We actually tried other approaches to prediction, many other approaches to prediction, but all of them were either too complex for practical implementation or not as accurate as the histogram approach that we took. So, and the final takeaway is that we've had positive initial results in production. So going back to our roadmap, now I'm going to talk about some of the work that we're currently doing and work that we're leaving for future work, but we intend to investigate as well. So going back to that little cartoon I showed on the 2 dimensions for improving serverless, let's start talking about some of the things that we still need in terms of making serverless the future. And the first one I'll talk about is running on spare resources. It's a great way to reduce costs for the serverless provider. And the reason for that, the reason why this is an interesting direction, is that FaaS or serverless lends itself nicely to spare resources that might come and go frequently because of the short duration of the functions. And spare resources are very cheap for the serverless provider to acquire from the cloud provider, because the cloud provider has an interest in using those resources, so it sells them at a very low cost, very low price. So we are investigating using what we call harvest VMs, and there'll be a paper in OSDI 20 about harvest VMs. Harvest VMs essentially are VMs that expand and contract on the nodes that where they land to use all of the unallocated resources, right? So if a harvest VM lands on a node and there are plenty of unallocated resources on that node, it expands to use all of those unallocated resources. So the key to take advantage of these very cheap resources is to adapt the scheduling of the functions to the availability of resources. And we've done work with, a student of Christina's actually, on a harvesting aware version of OpenWhisk. So we have a prototype of that, and it's pretty interesting. It does have good potential to reduce costs for the serverless provider. So another area that we're currently looking into is the need for fast state, right? As I mentioned before, if we want state to be used across invocations, it has to be persisted, typically in remote storage. And we're creating a cooperative in-memory cache that is quite different than the previous caches that have been proposed for a few reasons. First, it targets large state, like data frames, for example. It scales out for both compute and data transfers. It's transparent, tied to applications, so they can be pre-warmed with the application itself. So there's quite a bit of interesting work going on there. Another thing we're looking at is at task parallel computation, and in particular with the desk library for Python, and Rodrigo here, your general chair, and Joseph Valero have been looking at that in detail and trying to target task DAGs and large data in that context. And finally, we've been looking at end-to-end performance prediction in serverless and quality of service. And it turns out we have some initial results. Same Oniketi and folks from Purdue have results on being able to predict the performance of pipelines, workflows in serverless. And with these predictions, we can actually provide differentiated levels of service. So these are some of the directions. The final one, a couple more. So tiny VMs. Tiny VMs are really important in terms of achieving multi-tenancy. In other words, being able to have fast startups and safe multi-tenancy, where we can put functions from multiple customers in the same VM or in the same bare metal server in such a way that they are secure. They cannot interfere with each other as far as security. And we're looking at, resource oversubscription for these VMs for the case of the multi-tenant case. And there are many examples here of tiny VMs that have been proposed, like Firecracker and Hyper-V containers. Another aspect of our future work is also going to look at system and hardware support. In terms of the system, you might think of things like locality aware cluster scheduling or container scheduling on the node, where perhaps we go from time sharing to run to completion, for example, because functions are short, those kinds of things. And also the potential for hardware support in terms of container startup cross-container communication, and so forth. So in all of these areas, there has been some initial work, but we think that we have potential interesting angles there to investigate. Finally, the last one that we have as future work is trying to address the need for tracing and debugging tools, and those can enable the creation of more complex applications that can be more easily debugged, or enable application optimization, such as sort of being smart about what you keep in memory and how to schedule functions to maximize locality. So in conclusion, I hope that I was able to convince you that serverless computing can be the future of the cloud. But in order for us to get there, we have to make progress in at least two main dimensions: in broadening its scope and improving its efficiency. And there are many open challenges, as I mentioned, in terms of some of the future work, the current work and future work that we're doing, and many others are doing with durable functions and many other systems out there. And the cool thing about all this is that this is an enormous opportunity, especially for the researchers that are attending the conference today, people who are deeply interested in serverless computing. There are a lot of challenging problems to be solved, and a great potential for interest from industry as well. So thank you very much again for your attention, for inviting me, and I'll be happy to answer questions if we still have a little time.
Thanks a lot, Ricardo, for a fantastic talk. So yes, we have a lot of questions. I'll try to prioritize a few. So one question we have is, what happens when multiple invocations of the same function arrive at approximately the same time? Shouldn't a predictive scheme also determine how many containers are warmed up?
Yeah. So those are good questions, right? So if an application has a number of invocations that come together, that would be represented in the histogram as like a 0-minute idle time. That meaning that if there are a lot of them, we wouldn't load the application to pre-warm it later on, right? So we would just keep it in memory. And the second part of the talk, the question was, could you repeat that, Christina?
Sure. Shouldn't a predictive scheme also determine how many containers are warmed up?
How many containers? We could.
I think they mean if you have multiple invocations of the function, do you warm up all the containers that will invoke the same function?
Yeah, we do warming up per application, right? So all the functions of that application would be warmed together. That's one point. Maybe the intention of the question was also in terms of, well, if you have a large number of these applications, maybe you want to control the number of them that you pre-warm so that you minimize resource usage, right? If you're tight on space, for example. Yes, that's possible, but that's definitely not a scenario that the serverless provider wants to be in. So it will typically over-provision the amount of resources that it gets from the cloud provider so that it's never in that situation. But it is possible, yeah.
Great. Another question. So do you think serverless will move completely away from a container-based approach and towards tiny VMs such as Firecracker? Why yes or why not?
Yeah, using tiny VMs is sort of a requirement for multi-tenancy. Because containers don't provide enough security, right? Because the OS is shared. Right, so and the attack surface of an OS is much larger than that of a virtual machine, a hypervisor, right? So I I don't see containers being used when you want to maximize multi-tenancy and reduce resource consumption, right? You can always leverage containers if you keep users away from each other, right? So for example, you don't schedule functions of different users in the same VM or in the same bare metal server. That you can do. You get maybe a little bit more performance, but the tiny VMs are pretty highly performant anyway. So
great. Okay, what's the expected latency due to persistent storage services used with function as a service, such as AWS S3 versus Elastic file system?
I don't know the specific numbers from AWS, but you can expect milliseconds of latency. Definitely, we have numbers, although I don't have them in this presentation. We do have numbers for Azure Functions using Azure Blob as the storage substrate, and the latency degradation is significant. Like I said, especially for large data, because there are these I/O bandwidth constraints as well.
If I can sneak in a side question to that. So for applications that have multiple stages, where you have communication between different stages of functions, right now you have to go through a third party, whether it's remote storage or some controller. Do you see any possible optimizations for that, like remote memory access or something?
Yeah, there have been, people have been looking at that. I gave the example of durable functions, for example. Durable functions is geared towards sort of orchestrating, different workflows and so on, and sort of making the creation of workflows much easier. And they also have the notion of, state, small state. Other systems have done that as well. So people are looking at that. Yeah.
Mm-hmm. Great. So let me take a couple of questions from the Zoom Q&A too. So Anne is saying, thanks for releasing the workload trace. The workload is based on the current abstraction constraints in function as a service. But as pointed out in one slide, there is a push in improving the programming abstraction. And if there are new abstractions, the workload may change completely. Can you comment on that? For example, how useful is this workload for people who design new abstractions for serverless?
Yeah, that's a great question. So to make clear, the trace essentially shows the sequence of invocations and the amount of memory used and those kinds of things, right? The types of triggers and so forth. So it's very much a representation of how things are today, right? As new programming models become available, it will take some time for them to start to be used and be reflected in the type of trace that we produce. Now, whether it would be helpful to people who are studying programming models, we are collecting some data now. So before, I'm not sure we had very much, but now we are collecting some data in terms of communication between functions, right? How much functions are communicating. So people who do, who create programming models to facilitate communication, for example, could benefit from that information. But we haven't made it available yet. We're just collecting it in production now.
Great. One last question. Can you talk more about the function state management system you mentioned you are working on?
The function state, I think the person probably means the cache.
Maybe.
Yes. So yes, I can talk a little bit more. The idea there is to create a cache of this remote storage system to keep things in memory and tie it to the application. So in a sense, the cache gets loaded and unloaded with the application individually. So it scales really nicely because it's tied to the application. Another aspect of it is that, as I mentioned, we're targeting large data, right? So we may have a situation where either we stream data into the cache or we create multiple instances, each of which is going to take a different part of a large data frame, say. So there are some of these aspects that are quite different than what people have looked at so far. And the performance results that we've seen to date have been very good, right? And it also has like a simple consistency model and so on. Yeah.
Great. So there are a few questions, but unfortunately we do need to move on to the next session. So let's thank Ricardo again for a fantastic talk. Thank you very much for making the time.
Thank you. Thanks again for inviting me.
So early.